Okay, in this video we are going to be talking about the second fundamental theorem of calculus. And what happens is we're looking at taking derivatives of integrals and integrals of derivatives. So first of all, let's look at just the generic situation here. If we have capital F being the integral of lowercase f, in other words, it's its antiderivative, but we went from a number to x, what would have happened? You would have taken the antiderivative of little f and got big F and evaluated it from x to a number. So you would have had f, big F of an x, and then minus big F of a number, which would be some kind of number. But then if you took the derivative of that, okay, if you took the derivative of that, you would be back to f of x, and then this would be a number that you have calculated, and the derivative of a number is 0, so you would get f of x out in the end. And so we're talking about that relationship here. So in general, and there's going to be some stipulations to this, we're saying that if you take the derivative of an integral, you're going to get what was inside, because those two are going to reverse each other. And if you took the integral of a derivative, the same thing would happen. They're reversing each other's steps, so they sort of cancel out. Now, like I said, there's a little bit more to it than that, so let's get into some specific examples. Okay, so let's just start with examples 1 and 2. These I'm going from a number to an x, just like I was describing up there. And let's take the derivative of that. So the derivative of this can also be written like d over dx, integral from 1 to x of what you're looking at. And I started to write an x, and so this is a good time to talk about this. You can't have x here and x here. So you have t's here usually and a dt so that your variables all match here. And the x is coming in the limits where you would be plugging in when you took the antiderivative. So just know that. Now, since we're taking the derivative of an integral, we know those kind of cancel out. But because we were plugging in x when we took the integral, now this would be 2x squared minus 1. So basically, again, just look at what's in here, and because of the x that we're plugging in, that's going to change to an x instead of a t. Alright, so thinking of that in mind, again I have from a number 4 to x, and I have t's in here. So I can automatically jump. I know what's going to happen if I take the derivative of this. My derivative is going to be this with t's becoming x's. So natural log of x plus 2 to the x. And it seems too easy, but it's really just that. Just accept it and move on. We'll get to something a little bit more complicated in a minute. But again, I know that that happens when my bottom limit is a number and my top limit is a plain x. Now, what happens if the top is not a plain x? So I have a couple of those examples. Here again, that bottom number the bottom limit is still a number in 3 and in 4, but the top is something a little more complicated than just a plain x. What happens then is that you end up with a chain rule. So if I'm taking the derivative of this integral, I'm still plugging in whatever I had right here, just like I did a minute ago. And so this is going to become f of 5x squared. But because we're taking a derivative and this that we plugged in was not plain x, you have to multiply by the derivative of that limit, which would be 10x, just like a chain rule. Okay, so that was like the generic form. 4 has an actual function in there. So again, you want to plug in whatever that top limit is for the t's. So 2x x cubed minus 1 is what we get there. But then I'm multiplying the whole thing by the derivative of the x cubed. So I want to put this in parentheses because it has a minus, and multiply by 3x squared, just chain ruling it. Now, what happens if our lower limit is not a plane number? So everything we've done so far has had the lower limit being a plane number. Now we have to subtract, because when you plug in and you do the fundamental theorem, you subtract the top plugged in minus the bottom plugged in. So that comes into play here. But again, it's still kind of a shortcut. You're just doing the same thing we were doing. Since we're taking the derivative of an integral, we will have plugged in, so I would have f of 5x squared. Then because this is not a plane x, I would be chain ruling that part. And then I'm going to minus whatever happens down here. So since this is x, I'm plugging in x. And I don't have to chain rule this one because the derivative of x is 1. So I could put times 1, but it doesn't really affect anything. So you plug in and chain rule, subtract, plug in, and chain rule, if you have that. So down here, again, another example. The derivative of this, we would plug the 2x cubed all in for t, which means the whole thing is squared, so I'm going to put a parentheses around it. And then when I have to multiply by this derivative, I'm multiplying this whole piece by derivative, so I'm going to put it all together. Multiply by 6x squared. Then, because this is an x and not a plane number, I need to subtract, come on, and plug this x in. I didn't have to chain rule again because that one was plain x. Okay, so let's do some mixed examples. Our first example, we have a bottom limit that is just a number. It happens to be a pi over 3, but it is a number. Top is a plain x, so all I have to do is plug in x. So I'll have secant of x, tangent of x. Number 8, I have an x in the bottom and something with an x in the top. So when I take the derivative, I plug in. I have 4x plus 2 plus 1. Now the derivative of the top is 1, so I could put a big parentheses and put times 1, but we know that's not going to affect anything, so I'm not going to deal with that. I am going to subtract when I plug the bottom number in. Now, because this is a binomial, it has that plus in there, I need to put a parentheses around it. So 4x plus 1. Keep it all together. Number 9, not going to a polynomial type situation, but we do know how to take the derivative of that, so that's fine. Taking our derivative, since the bottom number is a 0, I don't have to worry about subtracting. I just have to worry about plugging in the top and doing a chain rule because this is not a plain x. So I'm going to plug in the top. I have square root of sine x, and then I'm going to multiply by the derivative of the top, which is cosine x. I don't have to subtract again because of that number there. Okay, I want to do one last example of this, and now I don't have a plain x as either one of my limits, so I'll have to chain rule both and subtract between them. So my derivative of this integral will be 1 over x squared times the derivative of the top, which is 2x. Then I'm going to subtract and do the same thing with the bottom. So 1 over tangent of x squared times the derivative of the bottom. So the derivative of tangent is secant squared. And you know, we're just doing this first step right now. Yeah, obviously with all this trig, you have identities that could make this simpler, and you would want to work those out if you were continuing this problem. But right now we're focusing on getting this process down. So that's about as hard as it gets, where you have two limits that are not plain x. You have to plug in, chain rule, subtract, plug in, chain rule. So that's how that second fundamental theorem works. Okay, so now we're going to look at another concept that's kind of related to all this, and this is looking at graphs, and usually they're stuff that can be figured out geometrically. So I have this graph here. I'm going to call it f of t, and yes, I know it doesn't pass the vertical line test, but it's easy to work with geometrically. So we're going to work with it. Now, we are given this purple information here. Says if h of x is the integral from -4 to x of f of t dt for -4 to 8, find the following. So h is the integral of this graph. So we're thinking area. But this has a specific number, -4, and going to x. So what's going to happen is they're going to give us different x's, and we're going to figure out certain areas. So if we start here, I have h of 0. h of 0, when I plug that in, means I have the integral from -4 to 0 of f of t dt. And so I want that area between -4 and 0. Well, that's just a trapezoid right here. And so if I know my trapezoid rule, 1/2 height, and this one's turned like we're used to seeing in geometry, so its height's 2. Base 1 is 4, base 2 is 2. I end up with 6 as my answer. So that one was pretty easy. Now, if I do h of 3, if I plug the 3 in, I'm looking for the integral from -4 to 3 of f of t dt. So I'm looking for that area again. And let's scroll back up here. Okay, from -4 to 3, 3 is right here. We already know that this area here is 6, and I'll even write that in. We just need this area here and this area here. So we have a square, a 2 by 2 square, so that would be an area of 4. And then we have a 1 by 1 square, which would have an area of 1. So I end up with an area of 11 there. If you need to write out those steps, you can. But it's easy geometry formulas there. Now let's do h of 8. h of 8 means I plug 8 in for x. So I'm doing the integral from -4 to 8 f of t dt. And if I come back up here, I figured out everything up to 3. So to 5, 6, 7, 8 over here, this would be 8. So here, again, I can look at it block by block if I want to, or I can look at this as a trapezoid, but it's a 1 by 1 block here, so I'm just going to write a 1. It's half a block here because that's a triangle with a base of 1 and a height of 1, so I'm going to say 1/2. And then over here I've got another trapezoid, so I'm just going to do all of that as 1/2, a height of 2, base 1 would be 3, base 2 would be 1, and so I would end up with 4. And because this is below the x-axis, I'm going to call that -4. So if I want the area all the way to 8, then I'm going to have 10, 11, 12 and a half minus 4. So that would be 12 minus 4 will be 8, but I have that extra half, so 8 and a half. So I can write that as 8 and a half, or I can write that as 17 halves. Okay, now for D and E I have these derivatives. The derivative at 4 and the derivative at 5, so that's where the second fundamental theorem comes in. What is the derivative of h? Well, based on this relationship here, h is the antiderivative of f. And so the derivative of h is f. So h prime of 4 is really f of 4. And we're looking at the f graph, so all I have to do is go to 4 and figure out the y value, and in this case that's 1. And similar situation if I was asked for h prime of 5. And so if I said h prime of 5, that's the same as f of 5. Okay, when I go to my graph, f of 5 is 0. Now, let's say for a second, and let's make a note here, that both of these were y values when you went back and looked at, when you come back and look at your notes, you'll know what we're talking about. Let's add an f. Let's say that we wanted to find h double prime of 5. Okay, what would h double prime be? If h prime is f, h double prime would have to be f prime. Okay, so when I look on the graph, since I'm looking at f, and if I wanted the derivative at 5, what am I looking for? I'm actually looking for that slope. And so the slope of this line, and this is supposed to be a nice smooth line, is down 1 over 1. Down 1 over 1, down 1 over 1. You can see that, so you can just count blocks. This slope is a negative 1, therefore the derivative of f at 5 is negative 1. So this would be negative 1. And again, I'm going to come back and make a note here. We were looking at the slope on that one. So you can talk about the original h, you can talk about h prime or h double prime in all their relationships to f, and see how that works out. And that concludes this lesson.